Alright, now let's continue on to problem 3, and this is looking at intersecting planes. So let L be the line of intersection of the planes, and then it has Cx plus y plus z equals C, and x minus cy plus cz equals -1, where C is a real number. And then in part A, we're asked, find the symmetric equations for L. And then part B states, as the number C varies, the line L sweeps out a surface S. And we're asked, find an equation for the curve of intersection of S with the horizontal plane z equals t, the trace of z in the plane z equals t. And then part C states, find the volume of the solid bounded by S and the planes z equals 0 and z equals 1. Alright, so this is a very complex question just to figure out what's even happening here. But if we go slowly, it all starts to make sense. So let's take a look at the solution to A. So A, we're asked to find the symmetric equations for L, the line of intersection of these two planes. And we could find the line of intersection L as in my earlier example. And here's a link to my earlier video on that. You could watch that. And basically, the first thing we'll do is first observe that the point -1, C and C lies on both planes. So when you have a point that's on the intersection, then we could find that line and so on. Yeah, basically, if it's on both planes, in other words, it's on that intersecting line. So what we'll do here is let's write the first equation. So Cx plus y plus z equals C. So Cx plus y plus z equals to C. And then if we write the second equation, x minus cy plus cz equals -1. So x, and then this is going to be minus cy, and then plus cz equals to -1. Let's double check that. Yeah, negative cy, cz, -1, and so on. So that's correct there. And what we could do is, well, we want to get rid of some of these, so we can subtract both of these. But first, what I'll do is I'm going to multiply C by the entire equation on the bottom here, and then subtract the entire thing here. So we're going to subtract C minus C on all this. So we just do some equation algebra right here. So we're going to subtract them all. So Cx minus Cx right here is going to cancel to 0. Then y minus right here, and so I'll just write that y minus c times cy, that's going to be, the negative becomes a positive, so plus c squared y, and then the next one's going to be plus z minus, now we're going to have a c squared z, like that, and then equals to c minus, and the negative, so it's c plus c. And yeah, get rid of the squared. Yeah, my mistake there. So it's a z, not a c squared, not z squared. So now what we're gonna get is I'm gonna factor out the c right here. C squared out. We're gonna have a y minus a z. So basically this and this, and then the next one's gonna be plus y plus z equals to 2c. All right. So now in this case here, if we want to vanish this right here, so let's take a case right here. If right here, if y equals to z, then we're going to have a c squared, let's go, it's going to be y minus, let's get, y is just going to vanish, like that, and then I'll just put it as y, so this vanishes to 0, and this is going to be, again, plus y, I'll put it as y, so you can just replace them together, equals to 2c. In other words, we're going to have a 2y equals to 2c, so in other words, y equals to c equals to z. Like that. Because basically we had if y equals z, and then we could plug that inside the first equation. So let's go 1 right here. So any equation. So the 1 right here, and we're going to have c x to solve for y. So plus y is c, plus c like that, plus, and then z is c. Plus c equals to c. This cancels, and we're just going to be left with right here, cx, move this over to the other side, equals to negative c. In other words, the c's cancel, x equals to -1. Like that. Yeah, so thus we get the point on both planes, and hence the intersection point is going to be -1 and C, like that. Alright, so now we have a point on both planes, and hence the line of intersection. That's -1, C, and C. And now another thing to note is we know that if you have, these are the equations of planes, and the equations of their normal vectors are included inside these equations. So put a note right here. So recall also that the normal vectors of each plane is included in their linear equations as per my earlier video, and here's a thumbnail of that video. So equation of the plane. So the dot product is a normal vector perpendicular to the plane. Dot product with r minus r naught vector like this. That's a point on the plane. Just 2 points on the plane, subtract it, and then you're going to have it like that. And then to dot product equals 0, you get this linear equation when you expand it out, and so on. And then the normal vector right here is this A, B, and C. So those are included in this normal vector right here. This equals to A, B, and C, normal vectors. So let's just obtain those, because we're going to need them. Yeah, so thus for our equations, we have Cx, the two equations plus Z, plus Y plus Z, equals to C. And again, that's this right here. Cx is plus Y plus Z equals C. The next one is X minus Cy plus Cz equals -1. X, and then this is going to be minus Cy plus Cz equals to -1. Yeah, so that's the normal vectors. I'm just going to write this as normal vector 1, and 1 of this one is included in there. That's just going to be C. Again, it's just in front of the 1. So Ax plus By plus Cz. In other words, we have right here, yeah, so we have the normal vector of the first plane, C, 1, and 1. And then the next one, and 2, this equals to, let's make this better line, like this. And this equals to -C, C, and actually no, there's a 1 in front, for the 1 for the Z, for the X. 1, -C, and C, like that. Alright, so we have these two normal vectors. I'm going to box these out. We're going to need them. Alright, so going further, so now since L lies in both planes, it is perpendicular to both the normal vectors n1 and n2, thus parallel to their cross product. And I will illustrate that soon. So recall the cross product right here is basically if you have two vectors, A and B, separated by an angle, the cross product A cross B is perpendicular to both. And yeah, it goes like that. And there's a right-hand rule for this is for the angle, curls in like that. And the cross product is written in determined form right here. And you can obtain, basically it's going to be this. And then you can obtain the cross product and so on by crossing out some stuff. So for example, this one right here, cross out this A times, A2, B3. And then minus A3, B2, and so on. And we'll do that as we go further in. Yeah, again, if you haven't just grasped on it, there's the formula there, and I'll show you the shorthand as we solve it. And just to illustrate this, so since L lies in both planes, so again, we have the two planes are intersecting, and we already solved the point that is on both. So let's say we had a plane like this. Let's say this is plane 1. This is, let's just say this is the plane 1. There's a line of intersection. Let's say it crosses like that. There's a line of intersection. I'll draw the line first, actually. Let's say we had a line of intersection like that, and we had a plane like this, and it's intersecting right on this line, but there's two planes right here. There's another one like here, crossing this, and it goes behind it. So it goes like behind it, this one goes below it, and so on. So there's two planes, and there's a line of intersection L, like that. And then on, let's say this is the first plane. Let's say the perpendicular vector to it. What I'm going to do is I'm going to draw it like this, and it's perpendicular to this one. So it's perpendicular to that, like that. And this is going to be called N1. And let's say we had another point right here on this one. Now perpendicular on this one here is going to be somewhere across, let's say it looks like this. This is, I'll draw it a bit further out. I'll just draw it actually here. Just to hide it away. So like that. And let's say this is perpendicular to this there. Like this. And this is N2. And then when you take the cross product of both of these, again, you could just shift these, superimpose onto itself. You're going to get again, using right-hand rule, That's going to be either up or down, but perpendicular to both. So this is going to be N3. I'll just go like this. I'll just put the N3 right here. So this is going to be perpendicular to both and is be parallel to the line. So this is going to be like this, N3, like that. Yeah, so in other words, read that again. So now since L lies in both planes, it is perpendicular to both the normal vectors N1 and N2, thus parallel to their cross product. So then this is going to be parallel to the cross product of these two right there. So we just solve for the cross product, and then we obtain the parallel vector, which is again a direction vector, and we could solve for the symmetric lines. So N3, let's solve for the cross product, equals to cross of N1 cross N2. And again, it doesn't matter which one you do first or the other one, you're just going to get a reverse negative or positive, but this along the same parallel segment there. So it's going to be like this, and I'll shift this over down a bit, and it's going to be I, J, K components. I, J, and K are the X, Y, Z components, like that. So that's that, and then the parallel vectors we had, the normal vectors C1, 1. That's it, C1, and then 1, negative C, C. 1, negative C, yes, C like that, and just cross it out. So basically now we could just solve for this, and then using the shorthand, you cross this out, cross the first segment there, and now we're going to multiply this by this, and subtract it by this, like that. So we're going to get right here, 1 times C is C, minus, and be a negative right here, becomes positive, and minus 1 times negative C, so minus a negative C, this is going to be C, like that, plus, this is the I, like that component. Erase this, do the same thing over with here. And now this part here is going to be a minus, because remember the cross product, it's going to be a minus, and then the next one's plus. And we do the same thing. Cross it out, we're going to go now C times by C right here, is C squared, minus 1 times 1 is 1, like that. And then this is going to be our IJ. And then plus, now the K1, erase this, cross this out. So now we're going to go C times negative C is equal to negative C squared, then 1 times minus 1 times 1 is 1. Like that, K. Like that. Let's erase this out and write this all down. I just write this in component form or in the vector bracket form, like that. C plus C is 2C. And then we're going to get negative C squared plus 1. And then this one's going to be negative C squared minus 1, like that. So this is our N vector, or N3 vector. And again, this vector is perpendicular to the normal vectors of the planes, but it's parallel to the line itself. So that's going to be used as our direction vector. Yeah, so thus we can obtain the symmetric equations of L. And there's a link to my earlier video as a thumbnail. So if you have direction vectors, so there's a line right here, L. And then this equation in vector form equals to R, so vector pointing to a point on the line L, equals to a vector pointing to a point on L, and then plus T, just a parameter T, times it by, a parallel vector, or direction vector. So V like that. So that's parallel to it. So that's parallel to it, like that. Yeah, I should have put a line like that, parallel to it. Like that. So that's that. But anyways, that's straightforward. So that, and this one is going to be A, B, C like that. And then the symmetric equations is just going to be, you take the components of these, add these up right there. So X naught plus T times A. And then Y equals Y naught plus B times T. Then and same for the Z. Then if you equate this as solve for T, move this over to the other side, divide by B. So you're going to get this, and then equate all the T's. And then again, you're going to get these symmetric lines. Symmetric equations of the line, and then you equate all the T's. So you get rid of the parameter T, and then you get these like that. Yeah, so in our case, we have, let's say our line L, it has a direction vector, like here, that's the parallel vector. This equals 2, and this is going to be our N3. This just equals 2. I'll put this N3 like that. In our case, and this equals 2C minus C squared plus 1. And then that's the next one, and then minus C squared minus 1, like that. And then the next part we need is just the X naught, Y naught, Z naught. Again, that's just a point on the line, and we already know a point on the line and that's over here, point -1, C, and C. So our P naught, this part right here, so P naught equals to -1, C, and C. So we have everything to make the symmetric lines. Yeah, so thus we have the symmetric lines. This becomes, we're going to have x minus x naught, this would be -1 minus -1 to be +1, divided by A is 2C. Like that, equals to, then now the y side, y minus C over B, which is -C squared plus 1, like that. And then this equals to the z side, z minus C over, then divided by this one right here, -C squared minus 1. And so we have that, but now Calculus book actually gets rid of this. There's too much negatives there, so what it does is well, there's negatives in the front, it multiplies everything by -1 and then gets rid of that part right there. So what it'll do is multiply by -1, so that just we get equals to x plus 1, just put the -1 at the bottom, -2c, and then equals to y minus c, and then c squared minus 1, and then equals to z minus c, and then c squared plus 1. So there's our symmetric equations of the line. And let's box this in. And now we have to have some disclaimer. So this right here, this works for all values of c except this is where we can't have c is equal to 0, otherwise it's going to be divided by, we're going to go approach infinity, so you can't divide by 0. So c is not equal to 0 for this, you can't use this equation. Not equal to 0, or, in this case here, if we have plus or minus 1, we're going to get a c, we're going to get a 1 minus 1. So -1 squared is 1, minus 1 is 0. So we can't have it plus or minus 1 like that. Alright, so since we can't use c equals 0, so this is symmetric equations for when c is not equal to 0 or plus or minus 1. But for those cases, we could solve those each manually or individually. So if c equals to 0, then the two planes are given by the equation. So let's write down our first equation, cx plus y plus z equals to c. And then the next one was x minus cy plus cz equals to -1. This is the equations of the plane we were given, or of the two planes. So we have those. And now, if we have c equals to 0, we're going to get a 0. It's going to vanish like that. C times x is 0. Plus y plus z equals to 0. And then at the bottom right here, we get, we're going to get a, we're going to get a x plus 0 equals -1. Like that. Yeah, so then this right here, we're going to get an equation y equals, move this z over to the other side, y equals -z. So y equals -z. And what I'm also going to do is, this right here is going to equal to x equals to -1. So our symmetric equations, so instead of the parameter looking like this, we could just, looks like this now. For this one here, we'll have x equals -1 and y equals z. So that's the symmetric equations for that. And now the next one is, alright, yeah, so the next case is if c equals to -1, so let's use that, just plug that c inside there, then the two planes are given by the equations. We're going to get a -1, x, so put the c right here, -1, we're just going to get -x plus y plus z equals to -1, like that. The next one at the bottom is going to be a x minus y, and then minus y, and then plus, or it's going to be -1, so minus, oh yeah, this is going to be c, this is going to be plus like that. So plus y is a negative c, and yeah, -1 times negative there. The next one's going to be minus 1 times z, like that, equals -z, minus 1, like that. Yeah, so we have that. Now what we could do is we could just subtract these. Well, actually, instead of subtracting, we could just add them. We could just add this this entire equation because we have a negative x and x right there. So we could add them up. This cancels out to 0, and we're going to get a plus y is going to be plus 2y. This right here is going to be, this vanishes. The z's vanish. We're going to get plus 0. And this right here adds up, equals to -2. So -1 plus -1 is equals to -2. So in other words, y is going to equal to -1. So this 2 and 2 divided by 2. So y equals -1. Well, instead of circling this, so y equals -1. And what we could do is now if we use this first equation right here and put that down right here and then plug in y equals 1 inside, so we get a like this. Put it like this. we're going to get negative x minus 1, for that's our y, and then plus z equals negative 1. Yeah, so what happens is negative 1 and negative 1 cancels, and move this over to the other side. We just get a simple z equals 2 x. Yeah, z equals x. So our symmetric equations now for this this case is just y equals negative 1 and z equals to x. Yeah, so that is that. Let's move this up like that. So there's that. And I just want to make a note right here. So note that the solution manual that I used from Calculus book made a typo in this part and is wrong. And you can I also double checked using GeoGebra graphing calculator. So anyways, so this is right. Whatever if you manage to get the solutions manual, that's wrong. And anyways, I'll just leave it at that. So because they made a typo, they put a negative somewhere where it shouldn't have been, or positive. I forgot what it was. But anyways, now the next one, the last one is if c is equal to 1. Because remember, this fits everything except these three cases. So if c equals 1, then the two planes are given by the equations. Yeah, so let's write this down. So if c equals to 1, so we're going to have 1, x plus y plus z equals 1. So that's the first equation, x plus y plus z equals to 1. The next one is going to be x minus c plus c z equals negative 1. So x minus y plus z. The c is equals to 1, just goes away. Plus z equals to negative 1, like that. And again, we want to subtract everything, so we get rid of the x right there, because it's they're both the same. So x and x, get rid of those, so we'll get a 0. This y minus negative y is going to be plus y, so we're going to get 2y like that. So plus 2y. Now the z's vanish. The z minus z is just vanish. Now 1 minus negative 1 becomes positive 2. So yeah, we're going to add, so negative is positive, so add 2. So in this case, we're going to get a y equals 2. Y equals 2, well, it cancels out, the 2's cancel, just equals to 1. Yeah, it's divided out and cancels it. So y equals to 1. And then lastly, so this equation 1, put equation 1 right here. Let's plug in y equals 1. So x plus 1 plus z equals to 1. So the 1's cancel. And we're going to get x and move it over to the other side. So we're going to get a z equals to negative x. So there's our symmetric equations for this scenario. So y equals 1 and z equals to x. Like that. Alright, and yeah, that's what we have. And note that the solution manual made a typo in this part as well, and then got the answer wrong. So this is right. Whatever solution manual got it was wrong. And again, we can double check all of our work using the amazing GeoGebra graphing, a 3D graphing calculator. So yeah, we can double check it by graphing in that the calculator, and here is the screenshots that I use. So here's c equals to 1, plane 1, there's the equation cx plus y plus z equals c, and then plane 2 is x minus y plus c z equals negative 1. And there is our line right here. You could just put in a line point right here, and then we'll have the that normal vector, or in this case going to be the parallel vector to the line, or the direction vector. And then it obtains our line like here, and so on. There's the line right here for the specific case of when c equals to 0, c equals negative 1, and c equals to 1. What I did was I just put points on it, and it formed the line on its own. So you could put negative 1, 0, 0, negative 1, 1, and negative 1. And then to do that, just to illustrate what I meant by that, is if you take this part right here for c equals 0. We end up having this right here. So x is negative 1. So x is negative 1. And then we're going to have, so x is negative 1 point right here. And then the next one is y, 0, 0. So if it's negative 1, and I just put another point. So if it's negative 1, I just put 0 and 0. So if y is 0, z is equal to 0. So I just picked the point on there. And then I picked another point, negative 1, and I put 1 and negative 1. So I put 1 as y, negative 1 there. And it automatically calculates the vector equation of a line. And I did the same thing for this one and this one right here. Just put points in it, and it automatically solves it. And then we can graph it out. So here is the line like this. And there's the plane in blue and red. And I'll play around with it soon in the actual website. And also here's the line L. It actually lines up with the equation, the symmetric equation that it was solving, and that lines up when you put c equals to 1 there. So let's go over to here. So here is what I've made, and then the other part of the equations are for the rest of this question. So there's the two planes. There's plane 1 in red. So what I'll do is some very interesting stuff. So here is initially there's nothing being plotted, or it's just C is being plotted. It's not really. Anyways, so that is the red is this plane, the first one, plane 1. Plane 2 is blue, and you can see is where it's intersecting like that. So it's intersecting right along that right there. And now if I could plug in the line, so there's a line from our point at -1 CC, CC, and there's a vector we put in there, the parallel vector or the normal to the normal vectors. So then put it in, and it exactly fits there. So again, this is how you double check your work. You just graph it as the third party graphing calculator, like this amazing GeoGebra, and it automatically solves that. I think that's how do I shift this over. Okay, shift it over here like this. Yeah, so that is that. And now what I'll do is now so this is just general one, but now if the line is L, I mean if C is equal to 0, we have to use a different equation instead of the symmetrical ones, but this one has a vector equation for this automatically calculated vector one. But here's an our case. So if I put this right here, it doesn't line up there. But if I change this if I move this around until it lines up, so I have to go all the way to 1. So there, notice how it's shifting around, it's curving. I we go to 0. Yeah, 0. So this is for 0. There's our equation. I just put the 2 points from it and go to 0. There's 0, and it lines up perfectly on it. And if I put the line, it exactly lines up with the line. So absolutely amazing. Now if I go to the -1, it's down there. So I'll get rid of this, get rid of this. Or actually keep it like, actually yeah, I'll just get rid of that. Actually keep it there. So -1, you go backwards, and then notice it's curving around, and lines up absolutely perfectly on it. It's absolutely amazing. So there's that. Alright, then that last one is 1. And I'll hide that. So notice how far away it is from the lines. And I'll just hide this line as well. Yeah, so it's far away from that. So you got to shift this over to 1. And so look, it's moving around. The planes are moving based on the value of C. There's a 0. And line exactly in line with that. So anyway, so the answers I gave are the correct ones. So many had different ones, and those would not line up because they're different. And I already double checked, and there's a line like that. It's absolutely amazing stuff. And again, to reiterate, these lines right here, for example, at L equals 1, I put 0, 1, 0. Well, I just put these two lines, and it automatically solves for it. All you do is put the points right here, 0, 1, 0, and 1, 1, -1. And to do that, so initially, if I go back to this one right here, so y equals 1, so y is always 1. Then I just put, let's say, 0 right here. It becomes 0. So we have 0, 1, 0. 0, 1, 0, and then another line I put was, this is going to be, let's put 1. So 1 is x, so z is -1. So we'll have 1, 1, -1. So yes, epic stuff. Alright, now let's take a look at the solution to part B. So let's go and read over that question again. Yeah, so part B states, as the number C varies, the line L sweeps out a surface S. And then we're asked, find an equation for the curve of the intersection of S with the horizontal plane Z equals to T. In other words, the trace of S in the plane Z equals to T. So I'll draw out what this actually is asking us to do. It's a bit out there. So let's first visualize the question. So we have the line L. So let's first graph a plane. What I'll do is I'll graph a plane like this, and we'll call this plane right here Z equals to T. So it's a horizontal one. Z equals to T, and let's say we had our line like this. So there's our line L. So we're asked, and then as you vary C, the L is going to move around, and it's going to form some sort of shape. So I'm going to draw this like this. It's going to form a surface around here, and so on. And I'm going to go put a line like this. This is, and then let's just move it around like this. I'll just move it all over, and this is at this point right here. So this is L I'll call LC2, this is LC1, etc. And basically it's going to trace out a shape as you vary the C value. It's going to trace out a shape. That's what we're, and it's going to be trace out a shape on this plane Z equals to T. And we can see this if we graph it out, actually. So here, this is the same link in before. I'll add the link as when we do the double check our work at the end of the question. So if we have this plane z equals to t, and initially z is 0.53, so there's the blue line, or the blue plane like that. And there's our equation L from the previous question part A. So there's our equation for the line L goes through the plane. Now what we'll do is, if we just modify C, we can just press the play button here, and now it's going to trace out a shape there. So we got to find out what the shape is. So it goes all the way here is 0.5, and it's going. I have it going backwards. It's moving around like that. At some C values, it moves faster, and it goes like that around there. So it looks kind of like a circle. So that's pretty cool shape there. So anyways, so first thing we got to do is, well, let's and find the, basically let's plug in, so if we set z equals to t in the symmetric equations and solve for x and y separately, we get, so basically we're going to plug in z equals to t inside this L and then find out what the x and y are such that where z is going to be on this plane. Yeah, so first let's take a look at the part A, the solution, where we had the symmetric equations. Yeah, so here's the symmetric equations, and what I'll do is I'll copy and paste these. Oops, like this. I'll copy and paste, and then we're going to plug in z equals to t. So move it down there, and paste it here. Alright, so what we'll do is solve for x and y separately in terms of t. So we'll equate this and this, and afterwards we'll equate the middle one with the z. So we're going to have right here x plus 1 over negative 2c. This equals to, well, z plugged in t there equals to t minus c over c squared plus 1. And now solve for x. Alright, so the next thing to do is multiply this out of there. So negative 2c, move it over to the other side. So this is going to be, we're going to get a x, and also move the negative 1 as well. Move the 1 over to the other side as well. So we're going to get an x equals to, this is going to be a negative 2c times it by t minus c, and then this is all divided by c plus 1, and then minus, this is going to be a minus 1. Minus 1 like this. I'll put a 1 like that, yeah, minus 1 like that. And also, yeah, I forgot to put a 1 there. So now we gotta just multiply this inside, and also what we'll do is get rid of the, we'll put them all under the same denominator. So multiply the top and bottom by c squared plus 1 over c squared plus 1. So that we'll have this inside. So this is going to become x is equal to negative 2c times t. Yeah, this is going to be negative, 2ct, and then move that in, it's going to be plus 2c squared, and now we have this right here is going to be subtracted by c squared, subtracted by 1, like that, multiply negative 1 inside, and then all divided by c squared plus 1. This equals 2, and this becomes, this is going to be negative 2c t, and then what I'm going to do is I'm going to write plus right here. This is going to be just c squared minus 1, and the solutions might just put this as a bracket there just because we're going to need this later. C squared minus 1 like that. And then c squared plus 1. Yeah, and this c squared is just because 2c squared minus c squared is just c squared, and then minus 1. So we have it like that. Let's put a bracket there just to group these together because it's going to be some next level stuff soon. Alright, so this is our x value, like that. Alright, now we'll do the same thing for the y. So we'll equate this and put plug in z equals to t there. Alright, so what we're going to get is, so y minus c, so I'll put this like this, y minus c over c squared minus 1 equals 2, and then t minus c over c squared plus 1, like that. And then move this over to this side and move this over to the other side. This equals 2. We're going to get a y equals to t minus c, or c squared, like this. We're going to get a, I'll put a t minus c, c squared minus 1, and then minus c at the end there, c squared, plus 1, and then minus, this right here is going to be c. So minus c, and then we'll do the same thing, multiply top and bottom by c squared plus 1 over c squared plus 1, and so on. Alright, so then what we're going to get is y equals 2, and we're going to FOIL this out. So this times this is going to be tc squared and then that times it by -1, negative t. Same thing now from the inside. Now we're going to go this times this, and then that times that. We're going to get a negative c cubed, and then a negative c times -1 plus c, like this. And then move these inside. We're going to have this one here. Actually, we made a mistake here. This was negative c. We moved it over as a plus c. So yes, that's a plus. Yeah, so that's a plus. And then what we'll do is right here. Yeah, so we're going to have to subtract or just plus this one, plus c cubed. And then plus c, like that. All over c squared plus 1, like this. Alright, just move it over like that. So now we're going to cancel some stuff out. So this cancels with this. And yeah, that's all we're left with. Now we have a negative t, and then this is a 2c there. But what I'll do is I'll factor out the t right here. So this is going to be equals to factor out t. So we're going to get a c squared minus 1. And then t. And then the next one is just plus 2c. So there's 2c's right there. Plus 2c, all divided by c squared plus 1, like that. So that's why in the first one we had the c squared minus 1. I should put that in a bracket because we have this one here as well. We can do some interesting stuff with it soon. Alright, so going further, so to eliminate c from these equations, we can work with squares, x squared and y squared. Yeah, we'll put the we'll work on this instead of just working it regularly. And again, this is a pretty next level a solution that we're going to go over. The solutions manual just gave the answer, didn't actually explain how it got here, so I had to find one online. So basically, what we'll do is if we'll let's write out our x equation right here. So we'll do the first one, x like this equals to negative 2c. Just put it all out like that, and then plus c squared minus 1 over c squared plus 1. So first what we'll do is divide this out, just separate the terms. So negative 2c like this over c squared plus 1. And because of the t value there, I'm going to put a t like this, and I'll move it over to the other side. This will make sense as we get through it. And the next one is the c squared minus 1 over c squared plus 1, like that. And this is going to be minus t, like that. Alright, so now note what happens here. If we look at these two terms right here, if we square and add them, notice what happens. And note, so if we have c squared minus 1, and you can kind of see the pattern that's going to arise, and then this is c squared plus 1. So if we square this, and then add the other one, 2c, like this, c squared plus 1. And then this is all squared up, move that bracket there. Plus c squared plus 1, all squared. Yeah, so what we end up having is, so if we multiply this top part here, c squared minus 1 squared, so that's going to be c squared times c squared, c4, and then c squared times negative 1, that's going to be negative c2, and then negative 1 times c squared, again put at negative 2 there as well. And then the next one is, this is going to be negative 1 times negative 1 is going to be plus 1. And then that's the top. And then this next one here is going to be plus, put them all in the same common denominator. Right here, 2c squared is going to be 4c squared. And now the bottom here, we're going to have c4, c squared times c squared. Yes, when you square c squared squared. C squared plus 1 squared. C squared times c squared is c4. C to the power 4. And then this one, c squared times 1. That's going to be c squared, and then 1 times c squared, another 2. So notice the similarities right here. And then this is going to be plus, and then this is going to be, yeah, the last one is just 1 times 1. Is 1. Alright, and now, see, notice what happens here. We have c4. Yeah, so we have c4 plus 1. So this matches up with this at the bottom. And this one right here, this cancels. We're going to get left with a 2. So 2c squared. So in other words, this entire thing equals to 1. So this all equals to 1. So that's that. Alright, so what we have now is basically a trigonometric identity. Well, we could write it as that. So what I'll do is I'm going to let this middle one right here, let this equal to cosine theta. And this inside as sine theta. So in other words, we're going to let c squared minus 1 over c squared plus 1 equals to cosine theta. Or cosine theta, and the next one is 2c over c squared plus 1 equals to sine theta. So if we let that equal to it, and then we just get the identity, we just get the identity right here. We're going to get cosine squared theta plus sine. So when we square this equals to 1, and then again, we already know this identity. This is already a trigonometric identity, so this is true as well. So we have that. Yeah, so that's what we have is, so we have that now. So I'll write thus x, now we just replace those inside. So this is our x value right here. So negative, this is c squared minus 1 plus c squared plus 1. So that's going to be cosine, and this is going to be minus sine, and there's a t. So this is going to equal to, it's going to equal to cosine theta, and then minus sine theta t. And likewise for y, because y has the same components, but just different order and so on. So if we go to the y is right here. So c squared, so this one here divided out. So c squared minus 1 divided by c squared plus 1. So that's just cosine. And then we have a plus now. So it's a plus like that. Yeah, except there's a t there. There's a t there. And then there's a 2c over there. So we'll move it around to the other side. This is going to be actually the other way around. This is going to be cosine t, and this is going to be sine theta. Move the sign in front. So there's the 2c over c squared plus 1. And that's our 2c over c squared plus 1 is sine. Move that over to the front so we have t on the other side. So there is our equations like this. Yeah, so we have these in this format, but what we could do is we could square them. So thus, or double thus. So if we square them, so we could apply this trigonometric identity to help cancel stuff as we'll go through it. So if we do x squared plus y squared and see what happens. So we're going to get a, because again, we've got rid of c. There's no c in this. There's a theta instead of c. So cosine theta is equal to these, and sine theta is equal to that. So we got rid of the c. And now we just got to simplify this further. So this is going to be a segment here. So cosine theta minus sine theta t. So square all that. This is going to be cosine times itself, like that. The cosine theta squared, and then cosine theta times this one. We're going to get a sine theta cosine theta t, and then do the same thing. Negative over here times it by cosine. We'll have a 2 there. And then this times it by itself. So negative, so basically, again, we're just foiling out, just doing it in our head. So negative sine theta times negative sine theta t. So we're going to get a plus sine squared theta t. Like that. And now do the same thing for the bottom right here. So sine theta plus cosine theta t all squared. So sine theta times sine theta is equal to, this is going to be a sine squared theta. The next one right here, this is going to be sine theta times cosine theta t. That's going to be, well, it's going to be a plus sine theta cosine theta t. And then likewise, what we'll do is multiply this out as well. So now going over this side, cosine theta t times sine theta, add another 2. And then multiply this by itself, plus cosine squared theta t. Alright, so what we end up having is, well, this equals to 1. This part right here equals to 1. This is just 1. Yeah, so put all of this equals to 1. Now this right here cancels. So we have there, which is canceled. It's going to be equal to 0. And then plus, right here now we have this sine squared theta plus 1 here. We can factor out the t. So what we'll get is a sine squared theta plus cosine squared theta t. So in other words, this equals to 1. So that's just equals to 1. So what we end up having is 1 plus t squared. That's all that algebra, and put this down here. So we got some epic stuff here. We get x squared plus y squared equals 1 plus t squared. And this is just a circle. This is circle. Circle of r. So r is going to equal to, well, the square root of this 1 plus t squared. And that's because when you have the x squared plus y squared, the right side is just going to be the radius squared. So it's going to be r is equal to 1 plus t squared. And it also has origin, and I'll write and origin. The origin is going to be at, well, in front of this one. Well, there is no x minus anything. So there's no x minus a or y minus b. So in other words, the origin is at the center. So origin is going to be at x equals 0, y equals 0, and it's all on the t plane because we're in 3D, so we'll just put a t. Like that, z equals the t plane. Yeah. Alright, then now we can graph this all out and as a way to double check all of our work using the GeoGebra 3D graphing calculator. So here is the c value where we can modify it. Here's the line. And basically, here is the t value. So we have t, you can modify it, and so on. And also, here's the surface S. When you plug it in, if you plug in z equals to t here, it just becomes a cylinder, a circular cylinder. And if you just put it as z as just a regular, just a variable, this ends up becoming a hyperboloid of one sheet. So notice, this is it becomes literally a hyperboloid. There's the shape right there formed by this line L. It's perfectly on it the whole way, and then as it rotates, it forms a circle. So it forms a circle like that. Yeah, so it's a circle there. If you put t as z equals to t, it becomes a circular cylinder, and I'll show that soon. Like that. Yes, that's what we have. And then also note here, note that the surface S, or which is just x squared plus y squared minus z squared equals to 1. Just move this over to the other side. Is a hyperboloid of one sheet. So it looks like this. So hyperboloid, basically a hyperbola on the top, like that, cross sections, and it's on every intersection. Even if you cut it along this this plane, like here on the y plane, you're gonna get another hyperboloid like that as well. And horizontal traces though are ellipses. So yeah, so if you cut it like this, you're gonna get an ellipse, but a circle is again a type of ellipse, a symmetric ellipse. You're gonna get it shaped like that, and so on. So ellipse or circle, depending on the type. And vertical traces are hyperbolas, and the axis of symmetry corresponds to the variable whose coefficient is negative. In this case, we have negative z. So negative z, so the axis is going to be the axis of symmetry there. So let's go and look at our graph right here. So this is right here is our graph. Yeah, so here's what we have. So first thing we can do is if you have the c value, if you modify c, notice it moves around, around in a circle there, but in a hyperbolic or hyperboloid of one sheet. It's always around there. Notice forming a perfect circle around this plane like that. Yeah, so that is our circular there. And going further, so this is the hyperboloid, and there's the horizontal plane z equals to t is in blue, so you can modify this, and you'll see it goes up and down. So modify, this is a value I don't need. Delete this one. This is the value I need. Okay, so there it is. If you move it up and down, just a circle apart in there gets modified. Like that. And also what we could do is, if we change this into a t, or I'll copy and paste this, so I'll put a t there. If you put a t, it just becomes a cylinder like that. A cylinder. So I'll change this back into z. I'll pause this and go to, this is going to be z. And yeah, so that's going to be our z. So that's a hyperboloid shape like that. So that's epic stuff there. And so I'll just copy and I'll duplicate this right here. Duplicate input t like here, and just stop here, and then t like that. So there's our shape there, and this goes directly inside that circle there. And yeah, that cylinder, it strikes right at wherever the plane is. So if we go change the plane, yeah, so it's a very advanced. Yeah, so you can see the plane going, changing the size of that cylinder, but always in line with this hyperboloid of one sheet. So it's epic stuff there. So I'll just hide that. So yes, amazing stuff. So you play around with that, and I will just save this. All right. So yes, that's pretty epic stuff there. All right, so now let's take a look at the solution to part C, and if we scroll back all the way up to part C. Yeah, and so read that out. So part C, we're asked find the volume of the solid bounded by S and the planes Z equals 0 and z equals to 1. Alright, so let's take a look at the solution here. So since we know the cross-section of the hyperboloid of one sheet, surface S, so again, the surface S is a hyperboloid of one sheet, and we know that the cross-section is a circle, and we know its radius, we can determine the volume, volume of S between the planes z equals 0 and z equals to 1. So in other words, we just have two planes, and then basically set up an integral. So if we have let's say our hyperboloid of one sheet like this. So it looks like I'll do a cross section right here. So let's say we had I'll just do the full thing like that. That's the full thing. So we're going to do two planes like this, and cut one of them there, and then one is slightly higher like this. So cut them over there, and then. Let's move it down here. So we have the shape like this. It looks a bit whack. This is z equals to 0, and this let's say z equals to 1, and we know the shape here is a circle. So we know this right here, and we know the area. That's just area is pi r squared, and then we just take a infinitely small thickness. We'll call that d. We don't even need to draw it. I'll just write this here as we know this area. A at z is equal to pi r squared, and we know r is equal to, or we know r squared. R squared is just equal to, if you scroll all the way back here, right here. So r squared is just equal to 1 plus t squared. But that's at z equals to t. But so in general, it's just going to be 1 plus z squared. Yeah, so it's going to be 1 plus z squared. So this is going to be pi 1 plus z squared. And yeah, for completeness, I'll just take an infinitely small thickness right here. So we take a slice like this. And alright, so there's a slice. I just drew it all over there. And this is going to be our dz. So basically, infinitely small thickness. So then that means we could just take our integral. Yeah, so this means that v is equal to the integral from, 0 to 1, the planes, and then az dz, like that. And again, that's the infinitely small thickness right there, dz, multiplied by az, so you get that infinitely small volume there, and we just integrate it over the entire length there, or entire thickness from z equals 0 to 1. So in other words, let's put the v here now. This equals 0 to 1, plug in our a and z, a of z, the area. It's equal to pi 1 plus z squared, 1 plus z squared inside. dz. This equals to, take integral, put the pi out of there. This equals integral from of 1 is just be z. And then integral of z squared is equal to z cubed over 3. And then this equals 2, well, and this is going to be from 0 to 1. The range 0 to 1, this equals to pi times it by, put the 1 there, 1 plus 1 cubed. And also multiply top and bottom 3 by 3 plus 1 over 3. And then minus, this all just vanishes 0, just like that. So then this ends up equaling, right here, v is equal to, so 3 over 3, is just, plus 1 over 3, that's just going to be 4 over 3. This equals to 4 over 3 pi. So there's our volume. Yeah, pi like that. Put this a bit neater. So pi. So there's our volume of the solid there. Alright, so yes, amazing stuff there.